Hello ladies and gentlemen, welcome back to GGS300, Quantitative Methods for Spatial Science. Today this is going to be the 6th laboratory and it's going to accompany the lecture which hopefully you watched already. So that was lecture 8 on inferential statistics and hypothesis testing. So hopefully you've been able to download the code which goes with this video, and hopefully you've been able to absorb the information which I presented in the previous session. So essentially those 6 steps that I need you to learn, please, which essentially dictate how you actually formally test a particular hypothesis which maybe you've posited for your research dissertation or some other form of research work that you're carrying out. What we're going to do today is I'm going to work through a little bit of our code and basically give you examples, mainly from the book actually, and then just kind of show you how we basically crunch the numbers based on some quite simple lines of our code, essentially to go through those 6 steps and then actually draw out some decisions based on the underlying test statistics that we produced for the data which we've obtained. So, without much further ado, let's get started. And you'll see here that in the first example that we're going to work with today, we're going to be focusing on this one-sided, one-sample difference of means test. So you should remember that we've covered this already within the lecture. We're going to use the Middletown example, which is in the McGrew et al. Book. It's actually on page 142. So you'll be able to just read it here. It should be section 9.1. It should provide you with a little bit of an overview. Essentially, we've got 2 different samples, and they're both taken for this fictional Middletown case. So we've got households, and it's regarding their average energy expenditures. Okay, so the amount that people actually spend on energy annually. We have 2 different samples. So we have a first sample, the largest sample of 250 households, which had an average energy expenditure of $1,821 with a standard deviation of $192. Okay, and then we have a second sample, and that second sample actually only has 25 households within it. That sample has an average energy expenditure of $1,810 with a standard deviation of 196. And then we have some survey data, okay? So we know that across the US, the average household expenditure on energy is approximately $2,000 a year, okay? And the question that we want to address here is, well, does this fictional town, Middletown, have a significantly lower average energy expenditure per household than the American average, okay? And hopefully from the information that we've been provided here, we can start to discern the different pieces of information that allow us to formally test this hypothesis. So let's begin. Essentially, we need to state the null and the alternative hypothesis. So the null hypothesis here is where mu is equal, so the population mean and the sample mean are both equal to each other, equal to the national average, so $2,000 per household. Whereas the alternative hypothesis is essentially where Middletown has a significantly lower level of energy expenditure than the average. Okay, so really the key point in that statement is that we're interested in whether it's significantly lower. So here we're definitely focusing on a directional hypothesis, and we're only interested therefore in what's taking place in the lower part of the distribution. Okay, so this is quite different from us just stating a non-directional hypothesis, which just says Middletown and the American average differ, but we don't say whether it's larger or smaller. And in that case, we would be looking at both ends of the distribution, so we'd be doing something slightly different. So this is kind of more of an easy example for you because you only have to worry about that alpha value existing in just one part of the distribution, in the lower part of the distribution here. So let's take the sample sizes. So the number of items that we had within the sample, n is 250. L here stands for the largest sample, so we'll work through the smaller sample later. So let's just start with NL for the number of data points that we've got. And the mean of this larger sample is $1,821 on average per household for energy expenditure, and the standard deviation for that larger sample is $192. Okay, and then we have a population mean mu of $2,000 on average per household. Okay. So we need to then select a test to use. Obviously, we're focusing here on just doing the one-tailed, one-sample difference of means test using a Z distribution because we've got more than 30 data points, so we can use the normal distribution, we can use a Z score, a Z statistic. And as we exogenously stated which test we were going to use in advance, we don't need to worry too much about selecting the right test here. We know we're going to use just this one very simple test, okay? Then on step 3, you'll know that this is where we basically set the level of statistical significance that we would like to use. And here we're setting an alpha value of 0.05. So we want to be 95% certain that the effect that we obtain if we reject the null hypothesis is true and that it hasn't just occurred by random chance. There will, as a result of this value here, it means that there's a reciprocal 5% chance that if we were to reject the null hypothesis because we think there's an effect, that it actually just occur randomly, okay? So I think we've covered this concept quite a few times now, but I think it's something that you kind of need to drill into your own head, the difference between the alpha value that you set and then the confidence level that you're going to have, okay? Then we need to delineate the regions of rejection. Okay, so first we need to find the critical Z value. So remember, this is one-sided, so we're just going to look in one end of the tail. As I've already mentioned, we're going to use Z because we've got a large enough sample size. So normally I think you'd probably always be using Z, but it's good to know what would happen if you were in a situation maybe where you really only had a small number of participants in your study, a small number of samples. And actually, I was thinking the other day, we actually have the benefit often of having large samples, but if you were testing as many of the fantastic vaccines that have been developed to address coronavirus, then for many cases, if a lot of people drop out, or if maybe you don't have enough data for one particular strata in your overall sample, and maybe because you don't have a complete, gender, race, socioeconomic breakdown, then maybe you've got less than 30 people, and then maybe you would, very much need to use that t-distribution that we spoke about previously, and which we will cover later in this session. Okay, great. So what we need to do is we need to get the Z critical value here. So we're interested in the value at which in the lower tail we have 5% of the values falling below and 95% of the values falling above, okay? And that's why we focused on the placing the lower tail value in this particular way. Yeah, don't get it wrong. I mean, I know we've been over this before, which way you should specify the lower tail. If you place it here with the lower tail being true, then that would be wrong because essentially we would have had the 5th percentile of the scores would be in the top end of the distribution, okay? And we don't want that. We want to be in the very bottom part of the distribution. So if the lower tail is equal to true, then we're finding the probability at the lower tail of a confidence interval, or if you want the probability of values no larger than Z. But if the lower tail is false, then you're trying to calculate the test value significance at the upper confidence limit, or you want the probability of values Z or larger, okay? So if you would like to input 0.95 directly, then you can, with the lower tail argument, then you can get the desired value that you want in the lower part of the distribution. So just think of this quite easily as give me the 95% of values that reside in the upper tail, okay? Great, so hopefully that's reasonably clear. I mean, I appreciate that this is quite abstract, so what I've done here is I've basically just plotted it for us. So essentially we have a sequence, this sequence here, this SEQ function just says, okay, from -4 to +4, give me all of the numbers at 0.01 intervals. So when we do that, we get a really long array of numbers like this, and we can actually just input that into a curve function here with all of these values, and we can generate this curve quite easily. So we've got all of the standardized scores on the x-axis here. So this is the a number of standard deviations away or above or below the mean, depending on which side we're on. And then actually what we can do is we can colour in our region of rejection, okay? So we can take our critical value, we can create a sequence out of it for that critical value, and then we can place these values as a polygon on top of what we already have, and then basically that area, that critical region of rejection, is really quite clear now for us to see. So if we go back to the value that we had for xcrit, which is minus 1.644, this is the minus 1.644 location, and then all of the values that fall below this value is in the region of rejection. So this should be approximately 5% of the values that fall down here, and 95% of the values which fall above. Okay, great. So let's continue now. We've completed this. Hopefully that's reasonably clear for you. Now I think what we've got to do is we've actually got to calculate the test statistic. Okay, so let me just go in the actual slides. Here we go. So how do we calculate the Z statistic as we want to do here? And you'll remember it's actually quite an easy formula in comparison to some of the things that we did last week. So we just need to take the population mean here and subtract it from the sample mean, and then divide it by the standard error of the mean. And that standard error of the mean is the standard deviation divided by the square root of the number of samples. So what I've got here is the population mean and the sample mean, so we'll subtract them to get the numerator, which is 179, and then we're going to divide that number by the denominator, which is the standard error of the mean. Sorry, that just missed. There we go, the standard error of the mean, which is 12.14. So it's at minus 179 divided by 12.14. And when we do that, we get minus 14.74. So it's really, really very, very much further below our critical value threshold. Okay, so remember that that minus 14 will be even all the way over here off our distribution of values. So very much so in this particular case, it's in the region of rejection. So as a consequence, we reject the null hypothesis. Remember, that's the way that we need to posit this. The null hypothesis is the baseline. It's the business as usual case. And what we're doing, because our value is in the zone of rejection, is we're actually rejecting that null hypothesis, concluding that evidence exists that our hypothetical Middletown residents have lower energy expenditures than the American average at the 95% confidence level. Okay, so the reason why I added that on the end there is because we have an alpha value of 5%, it's 0.05, which means the reciprocal confidence that we have, the complement of that probability, is 0.95, 95% confidence. Okay, so hopefully that's reasonably clear for you. You've got the example here to work through. We can now just validate, if we install the required package here, we can validate that number against an inbuilt test, which basically produces, or should ideally produce, the same results as what we've just generated. I've worked through manually how we obtain these results, but actually if you go to this zsum.test function, it produces essentially exactly the same result that I obtained. So the Z value here is minus 14.741, which broadly matches up with the Z calc that we've got here after rounding to 3 decimal places. Okay. And I think the key thing is that in the end of the lecture, I started talking about p-values, and here we've actually got a p-value. It's incredibly small, so very much below the 0.05 significance level that we were looking for. And this is indicative of how we're going to be using this type of thinking as we move forward. We'll be using p-values rather than formalized hypothesis testing, but you can see now how these two are directly related. Okay, great. So let's move on, and we will now start thinking about one-sided sample difference of mean. So this is for our smaller data set. So essentially we've got 25 samples, we've got our sample mean, we've got our sample standard deviation, we've got our population average, and then essentially we want to select the same statistical test, but this time because we've got less than 30 values, we obviously need to use the t-distribution, okay, so not the normal distribution that we used before. We are going to use the same alpha value of 0.05, but we therefore need to delineate our regions of rejection, okay, so we can use the quantile function here for the student's t-distribution. We can essentially enter the values that we have, so we want to be working at a 95% confidence rate. I want to get our t-critical value, which is minus 1.71. Okay, and sorry, I'll just delete this. Here we go. And then we can move on to start thinking about delineating our regions of rejection. Okay, so we've got our t-critical value here. Got our curve. So I'm just running through this again to give you an idea of how we are mapping that particular area that we're interested in. So the t-critical value in this case is minus 1.71, which means that this line here where the red part starts is minus 1.71 standard deviations below the mean because we're in the bottom part of the distribution, which means that at the alpha value of 0.05, 95% of the values are going to be above this point and 5% of the values are going to be below this point. Okay, so now what we need to do with the test statistic is we need to get the numerator, which is we need to subtract the population mean from the sample mean. Fine, that's fairly straightforward. We get 100 minus 190. But then we also need to get the standard error of the mean. So we need to take the standard deviation, divide it by the square root of the sample size. Okay, and when we do that, we end up with a t-statistic of minus 4.846939. Okay, so again, very much in our zone of rejection for the null hypothesis. So this time we will be somewhere over here just by the y-axis. And as a consequence, we're in the zone of rejection, therefore we reject the null hypothesis and conclude that the evidence exists that in our fictional town, Middletown, the household residents have lower energy expenditures than the American average at that 95% confidence level. Okay. Great, well I hope that that's reasonably clear for you. Now we can just check those numbers based on the inbuilt function which we've got. So we had the t statistic here generated as minus 4.84, and when we actually run the inbuilt function we're getting minus 4.84 again. And importantly we're getting quite a small significant p-value as well, which is indicative of this being significantly different than the population mean. Okay, well, fantastic. Let's move on now, and we can start to think about the different proportion approaches that we have, so the different statistical tests for testing the proportions of our sample relative to the population. And you remember that I covered this already within the lecture. So now let's just carry out some hypothesis testing using this particular approach. So we're going to go to 148, page 148 within the McGrew et al. Book. Middletown essentially is concerned that the proportion of housing units that are underwater is higher than the national proportion. So essentially underwater here is that you've got negative equity on your mortgage. So let's assume that you can buy a house for $100,000, which would be nice. And let's assume that you put $5,000 down, so a 5% down payment, and you borrow 95% of the value of the property. So the bank lends you $95,000, you put down $5,000 and you buy the house for $100,000. If because of COVID or some other financial crisis, there's a huge recession, people are unemployed, housing purchases fall, and that means the house prices fall, and maybe your property value is now worth only $80,000. That would essentially mean that you are in a negative equity, unfortunately. Obviously, a very sad situation to be in, but essentially it means that you owe more on your home to pay off the mortgage than what the home is actually worth. So that's essentially the definition for what we mean here by underwater or negative equity on the mortgage. Okay, so I hope sincerely it's a situation that you and I never have to be in. So imagine there are 85 housing units that are sampled within this fictional town, and 25 of them sadly are underwater, so in negative equity, giving a sample proportion of 0.294, so 29.4% of houses are underwater. The survey nationally shows that the proportion is about 0.228 nationally, so 22.8% of homeowners are in negative equity. And essentially, that means we can state our null and our alternative hypothesis. So if we think that there's no relationship between Middletown and the rate of negative equity relative to the national mean, then we would say there's no difference, and therefore there would be the sample proportion and the population proportion would be the same. Okay, they would be equal. But the alternative is that the number of residents in Middletown are actually, the proportion of residents in negative equity is higher than the national average, and by that we obviously mean it's directional, and that means that we have a very specific approach to how we need to state our alternative hypothesis. Okay, so this very much just focuses on the proportion being higher than the national average. Okay. So let's now put these numbers together. We have the proportion in our sample. We have 85 housing units overall. So it's the number of sample points that we have, 85. We then have the number of underwater, so financially negative equity based homeowners, which is 25. And we can get the sample proportion by dividing that and basically getting the results, which for SP is 0.294. So that's great. That matches what we said previously. The population proportion nationally, we know from the survey data is 22.8%. So 0.228 is the proportion, and that gives us our metrics of interest here that we want to test. We know that we're going to be using a proportion here because we stated that at the beginning, and we're using the Z statistic because that's the standard way for us to carry out our proportional testing. We want to be 95% confident that our result hasn't just occurred by chance, so we have an alpha value of 0.05. So if our value exists in that portion of the lower tail where the 5% of values sit, we can be 95% certain that the results haven't just occurred by chance, and there would only be a 1 in 20 chance that the result just naturally occurred by random. Okay. We can then begin to actually delineate our regions of rejection. So we're using the Q-norm function again. We're stating that we want it to be for 0.95. We're getting the critical value, which is 1.64. And that's positive, so that's standard deviations above the mean. And then we can actually identify the area of rejection, which here is in the positive part of the distribution before. In the positive part of the distribution this time relative to before where we're in the lower part. So we have our Z critical value, which is 1.64 here. So this vertical line is the 1.64 standard deviations above the mean, which means anything above this point, which will be approximately 5% of the values, will be within our zone of rejection for the null hypothesis. Okay. So now we've got that, we can actually calculate the test statistic. So if we go back to the test statistic formula, what we need to do is subtract the population proportion from the sample proportion divided by the standard error of the proportion, which we get based on taking the square root of the proportion multiplied by its complement divided by the number of sample points that we have. Okay, so the way to do that is row multiplied by 1 minus row, so this is getting us the standard error of the proportion, which in this case is 0.045. So that's a fairly simple equation. It's this one over here on the right hand side. And then essentially we're able to create the test statistic. So the denominator of that is the standard error of the proportion, and the numerator is the sample proportion minus the population proportion. And when we actually we make that calculation, we get 1.45, which is not within our zone of rejection. Okay, so our critical value was 1.64. Up here, we're not in this zone of rejection this time, we're somewhere around here. So we are in the upper part of the distribution, but we do not go into the zone of rejection. So, as a consequence, therefore, we fail to reject the null hypothesis. This means that we do not have enough evidence at the 95% confidence level to show that Middletown's underwater rate is any different from the national rate. Okay, so that's the way that you want to basically report your findings here. There's not enough evidence to reject the null hypothesis. Okay, and that's the kind of key statement that I'm going to be looking for when you're made to report these statistics, because it's indicative of the fact that you're aware of how this particular statistical approach works, and that we need to be very careful in how we actually word the findings that we obtain from these statistical tests. So let's just check using one of the inbuilt tests if we are able to actually obtain this similar statistic. So we don't actually have an inbuilt function specifically to test these proportions, but we are able to, use this particular proportion test here. And what it produces is a chi-squared value, which here is 2.11111. And essentially the chi-squared value is very similar. So essentially it's just a squared version of the z-score. So we can actually just take the square root as a consequence of that. And when we do that, what we end up with is the 1.45 that we calculated manually just up here. So hopefully if we look at the zcalc, it's 1.45 here. That matches our inbuilt function 1.45, demonstrating that we were able to calculate correctly in a manual way this specific test. Okay, so hopefully you've got all of the information that you need now to run through these different materials within on your own computer, and then within this particular lab session. You've got the book in order for you to kind of gain the higher level theory. You've got the code for how we've tapped through those different hypothesis testing approaches. And you've got assignment 6, which also will be due a week from today, so 7 days, which, just to clarify, is definitely March 25th. Okay, I think I said 26th in the last lecture, and that was just a mistake on my part, so my apologies. So that will be due on the 25th, and I look forward to hearing from you. If you've got any further questions, don't hesitate to reach out, and good luck with it all, and hopefully you'll be able to excel at this, and then we'll be able to get into some more advanced tests in the coming weeks. Okay, well, thank you very much for tuning in, and it was great that you were able to take part in this lab today, and I look forward to seeing you all again soon, hopefully. Thank you. Goodbye.